Spanning tree protocol. Layer 2 networking is considered by many to be the optimal technology to build a complex LAN on. It has the advantage of speed over Layer 3 devices like routers, and it adds addressing, which gives it an advantage over Layer 1 devices like hubs. But one of the biggest problems with Layer 2 addressing is that it lacks the native support for redundant links. Spanning tree protocol gives that redundant link functionality to Layer 2 networking. In this nugget, we're going to start off with a definition of exactly what spanning tree protocol is. Then we will list the port states that are associated with a spanning tree protocol port, and then we're going to break out the bridge protocol data unit and discuss its function. Next, we will outline the route election process, and after that, we're going to look at how the route path cost is calculated. A discussion on route and designated ports will follow that, and we're going to end up by defining what convergence is and looking at the causes of it. Our definition of the spanning tree protocol is going to start off by talking about its main purpose, and that is to allow link redundancy while at the same time preventing layer 2 loops. So let's see how that might happen. Here we're going to have a typical network setting. One switch in the middle, each of these squares represents a switch, and we have links between them. Here we're going to have some redundant links from one primary network location. So this is a network here, local area LAN, and it has two links that it could use to get back to the center of this network topology. Now those two links are going to be allowed to be configured, but the spanning tree protocol is going to take the two and compare their costs, and by the comparison of the costs come up with one that will be allowed to forward traffic and another one that will block traffic. This is as simple as a spanning tree protocol gets. It's simply going to compare the cost, allow one to forward, and set the other one in blocking mode. If for some reason this path were to go out, then you have another path, a redundant path that can be used in the case of that failure. And so now this path would be allowed to forward, and this would be blocked not by choice, but because of some other circumstance. The awareness of the spanning tree protocol does not operate above layer 2. So recall from our OSI model conversations, we have the physical layer, and then we have the data link layer at layer 2, and this is where spanning tree resides, here and below. So the network layer, or the layer 3 addressing, has no idea that spanning tree is operating underneath it. The spanning tree protocol, like ice cream, has been defined in many different flavors. Now the Cisco devices are going to use the IEEE standard of the spanning tree protocol, which is 802.1d. Remember that IEEE is a standards organization. So they came up with this specification, and it's in use in all Cisco devices that have layer 2 functionality. At this point, let's jump into a switch. This is a 1900 switch, as identified here, Catalyst 1900. And what we're going to do is understand how we can enable or disable STP. The first thing we're going to do is opt for M for the menu option. And then we're going to get into the network management portion. Once that's done, there's a category, bridge, pretty much defined as spanning tree protocol underneath the bridge. Now understand that 802.1d, as you read it, it's going to have a lot of terms in there that reference the bridge. There's going to be a root bridge, there's going to be a bridge ID, things of that sort. At the time that it was developed, the bridge was really the only layer 2 device that they had. So it seemed okay to name these different objects within spanning tree after a bridge. Since switches have come out, which are layer 2 devices as well, they have not changed the naming. So when I say bridge ID, that can be used on a switch. Or if I say the root bridge can actually be a switch. So don't get confused on the terminology. Now let's go into option B there, and we're going to look at spanning tree of a VLAN. Now again, we have the 1900 switch here. It tells us which VLANs are enabled with spanning tree, which is 1 through 64. But what we want to pay particular attention to is the ability down here to either enable spanning tree or disable spanning tree, and it's on a per VLAN basis. As you know, whenever you set up a 1900 switch, all the ports on that switch are going to be on one VLAN, and that's VLAN number 1. So if I opt here to disable spanning tree, it's going to show me a little brief introduction about what the command does, and it's going to ask me for a specific VLAN number. If I set 1 in that field, hit enter, then I'm going to now see that my VLANs with spanning tree enabled has changed. It used to be 1 to 64, now it's 2 through 64. So it's easy as that to turn on VLAN or spanning tree for specific VLANs. Now I'm going to go ahead and enable that for VLAN number 1. That was the E option, and now VLAN 1, and you see that it's changed back 1 through 64. So with that, when we discuss the different terms that are involved in spanning tree, like a root bridge, there's going to be 1 per VLAN. Keep that in mind because it's very important. When I defined the main function of the spanning tree protocol, I talked about interfaces being placed in a forward state or a blocking state. These are two of the 4 states that are allowed on a port basis for spanning tree. Let's look at the rest of them. The best way to look at this is we're going to assume the 1900 power up process. First, we're going to turn the device on. As soon as you turn the device on, all of the ports that are involved with that 1900, normally there's 15 of them, are going to be set into the blocking state. Now, the blocking state means that we are not going to be forwarding any traffic out of that port. So if I have a port here, as I power this device up, these ports are not going to be allowed to forward any traffic, because remember, we don't know yet which of these links are redundant. So if I just start forwarding traffic out, I might create a loop, and the main purpose is not to allow loops. All right, so I'm blocking. At that point, we look at the configuration. There's 2 options for every port. Either they are configured, and this is administratively configured, as disabled or enabled. If they're disabled, we're done at this point, because there's no sense in having a state for a disabled port. If they're enabled, though, the process is going to go as follows. The first thing we're going to do is have that port move into a listening state. And what it's going to do there is it's going to listen for messages coming back saying that you should be in a blocking state. So there are specific messages that it can receive saying, go back to blocking. It's going to wait a predetermined amount of time that is known as the forward delay timer. So we got a forward delay timer. Now this forward delay timer by default is going to be set to 15 seconds. So it'll wait 15 seconds for the devices to let it know it should be in blocking state. If it's not received, in other words, no news is good news, then it's going to move into the next state, which is the learning state. At this point, it's still not going to forward information out onto the wire, but it's going to listen and learn from the information that's forward between other switches to figure out where it fits in the topology. The information gathered there is used to build up a database, and it's called the forwarding database within the switch. Now, the delay timer that we use within the listening state is also going to be the same timer we're going to use in the learning state. In other words, we're going to learn for a finite amount of time, default 15 seconds, and then we're going to move into the forwarding state. At this point, the ports are allowed to send and receive traffic freely, any traffic that is designed to traverse over these layer 2 devices. Let me show you where we would find the state of each port within a 1900 device. We're going to back up here. Notice that I can use the X key to go up to the previous menu. So I'm going to go up to this menu here, and then we're going to opt one more X to go up to the main menu, and it's identified here as the main menu. I'm going to go into port configuration, the P, and then I'm going to define a port. I want port 11. Hit enter, and the first thing it's going to give me, well, one of the first things, is the fact that we're working in 802.1d, which is always going to be true with any Cisco device and spanning tree, and then it gives me the state. I am in the forwarding state at this point. Remember, the other states could be blocking, listening, and learning. Now, this is going to be true of every port. So if I go down here, and I can opt for next port or previous port, I'll do previous port, you're going to see the same kind of read for port number 10 now. As the layer 2 device advances between each of the different states, listening to learning, learning to forwarding, we had talked about different messages that had been passed between switches. Here at the listening state, you are waiting for a message to come back and advising you to go back to the blocking state. In the learning state, I'm building a database. I have to have information to do that. The way that these layer 2 devices exchange information, specifically management information, is called a Bridge Protocol Data Unit, BPDU for short. On the left here, you see a breakout or representation of the different parts of a BPDU. Let's go over them if we can. First of all, the protocol ID is going to be 2 bytes in length. This is going to show you the length here, and this is the actual field. 2 bytes in length, and it is always set up as 0. So in other words, it's not used. Then we have the version ID. 1 byte in length, the same thing. It's going to be set up as zeros. Finally, we get to the type ID. This is the first pertinent piece of information we're going to get out of the BPDU. Now, different type IDs are going to be represented. If we have a 0 here, though, that's going to represent a configuration type of BPDU, and it's the one that we're most concerned with, especially at the states that we're talking about, moving in between states. That's going to be 1 byte in length. The next thing we have is the flags, and then after that, we're going to have the root bridge ID. This is rather large, especially in comparison to the other fields. It's 8 bytes in length. And that's because it's made up of 2 different parts. Now, we're going to get into a discussion now of bridge IDs. So let's drop the root for a second and just have the bridge ID discussion. A bridge ID is made up of 2 parts, as I just said. The first is a bridge priority. Now this is going to be 16 bits, in other words 2 bytes long, and this bridge priority is used, and it's the first measure used to select a root bridge, which we're going to talk about a little later in this discussion. But understand there's a bridge priority, and then the next part of this is going to be the MAC address. This is the physical address that exists at layer 2, and it's 48 bits long. You're familiar with this from earlier nuggets. These two pieces of information combined are the bridge ID. So what we have here is the bridge ID of the root bridge. Again, we're going to talk about the root bridge a little later. Next, we're going to have the root path cost. This is going to be 4 bytes in length, and what it does is it tells you I am so far from the root bridge, and it's going to tell you that in cost. This cost is identified by bandwidth of the links between the switch that's in question that's sending out this BPDU and eventually the root switch, and whatever's in between here is going to be identified in this cost. All right, and then the sending bridge ID, again, it's a bridge ID, but it's the bridge ID of the sending device. And then we have a port ID. The rest of these are used within, or timers, things of that sort, used within the configuration of STP. And then the last thing we see here is the forward delay. This is going to be 2 bytes long, and it's the timer that we talked about between the different states. Before we leave this section, let me talk a little bit further on the bridge priority because it is so important. The range on the bridge priority is between 0 and 65,535, which means that we have 65,536 possible values for this bridge priority. I've stated over and over that the bridge priority is important, but now we need to understand how it's used. In other words, what makes it so important? Here we're going to have a slide talking about the root election. Now the root is short for the root bridge. We talked about this earlier. 802.1d defines all of these terms in reference to a bridge, but a root bridge can be a switch. This is simply the central point of the network, right here, the layer 2 network that is. And now the root election is a process that happens behind the scenes to define that switch that's going to serve as that central point. Don't get confused here though. When we call this the central point of the network, we're not saying that all data has to run through the switch. It's the central point of the STP network. In other words, it is the central point of the management process that is going to make sure that we don't have any loops within our environment. In other words, like we said in the definition, we can have redundant links, 2 links leading to the same place, but we're going to shut one down and allow the other one to forward traffic so that we don't have any loops in our environment. Now on to the election process. Each one of these layer 2 devices, whether it's a switch or a bridge, is going to send out a BPDU. Now within the BPDU that it sends to its directly connected neighbor, it's going to identify the sending bridge ID. Remember we saw that in the BPDU whiteboard we saw earlier. The bridge ID is going to contain the bridge priority and the MAC address of each device. So what we're looking for is a differentiator between this bridge ID so that we can say, hey, one person or one switch, I'm sorry, is the root bridge. And the way we're going to do that is the bridge priority is set to a certain number. The default is 32,768, which is by chance, not even by chance, exactly in the middle of the values, the 0 to 65,535. Now, each of these is set by default, and so if there is no difference in the bridge priority within this whole environment, in other words, every Cisco device has this number value for a BP, then you're going to move into the MAC address. The layer 2 device with the lowest MAC address is going to be set as the root or the center of our STP network. Adhering to this process of selecting a root bridge leaves a lot up to chance, because you've got to understand the root bridge doesn't have to be your most powerful layer 2 device or your most powerful layer 2 switch if you're dealing with all switches. It has to be your most centrally located. And think about the fact that the MAC address, the lowest MAC address, might actually exist on this layer 2 device here. And now your root or your center of your STP domain might actually be on the fringe of your network. And not that it won't operate, it just wouldn't operate as cleanly. So the recommended process is to manipulate this bridge priority so that you can pretty much assign which of these devices is going to serve as your root bridge. Let's see how we would do that. Jumping back into our switch, we're in the main menu here, and what we're going to opt for is N for the network management portion, and then we're going to go into B because this is specific to span and tree. Once we're in there, we see some configuration options, 1, 2, 3, and 4. These are just packages of bridge configuration. Let's look at the first one. So we hit number 1 here. And what it's going to show you is B for bridge priority. For this optional group, we can set the bridge priority by selecting B. You see the default, 32,768. I hit B. And what I'm going to see is my range and then a little blurb about what this bridge priority is used to do. So what should I set this at? We've talked in our discussion that we want to change the bridge priority so that we can manipulate one device to be the root bridge. But how do we know what number to change it to? In the world of bridge priorities, a higher bridge priority, and this is truly the way it's termed, nothing I can do about it, we just have to understand it, a higher bridge priority is actually a lower number. Okay, so let me explain it this way. If every device in this switched network had a default bridge priority of 32,768, except for this one here, and we set it to 32,767, then we have a winner. This is going to be the center of your STP network. Obviously, we don't want it to be the switch. We would set it here more than likely. But I just want to illustrate that the lower number has a higher priority. Going back to our device then, let's go ahead and type in, move my mouse up, 32,767, hit enter. And that's all you need to do. Now you're going to see your new bridge priority set up here. At this point, you might have somewhat of an uneasy feeling. Let me explain why. We are setting a bridge priority. Naturally, you would think in your mind, this is a global type of setting. In other words, if I want my switch to operate as the root bridge in an STP domain, I probably will set this number once for the whole device. But it's not true. I am setting one instance of STP per every VLAN. So here I see that this optional group affects VLANs 1 through 1005, which really is every VLAN we have on this switch. But let's say that this VLAN group and this option was assigned to only VLAN number 1 and number 2. And then once I exit out of here, we could have option number 2 here. I'm going to hit the 2, set to VLANs 3 and 4. Now, if I did that, the situation we could have is that I could have a central switch here being the root bridge for VLAN 1 and VLAN 2, and then some other device as the root bridge for VLAN 3 and 4. There might be times within your network that you want this configuration ability, and that's why they have those optional groups available. So far in this nugget, we started by defining exactly what the spanning tree protocol was. Then we looked at the different port states, saw the management messages in the BPDUs, and then looked at the root election just now. Now we're going to move into the root path cost. The root path cost is a number that's going to show you or signify how far a specific layer 2 device is from the root bridge. Remember, we just had the election, so we've identified this device as the root bridge. We have connectivity extending from this root bridge out to many devices. Again, it's central to our network. And in these devices, we're going to have some environments that show us loops. And those loops have to be turned off. And the way we're going to do that is by learning or identifying all the links, identifying the root path cost, comparing root path cost, and understanding we have loops that are potentially there, and then shutting those interfaces down to present the loop and allowing one to forward. In other words, like we said in the beginning, one would be allowed to forward, the other would be in a blocking state. So let's see how we're going to calculate this root path cost. Extending from the root bridge, we have gigabit links, 1 gigabit per second on this link. Here, we're going to have 100 megabit links. Here we have a 100 megabit link as well. And in here, we're going to have a 10 megabit link. This is the bandwidth associated with our topology. If we come down here, we have port speeds and then STP costs that are associated with those specific speeds. There's a simple equation for figuring out the default STP cost associated with each port speed, and it is 1,000 divided by the port speed in megabits per second. So let's see how this would work out. If I have 1,000 here, and I want to divide that by this link, which is 1 gig, essentially 1,000 megabits. Obviously, the M isn't important, just for your frame of mind. Then I have 1,000 divided by 1,000, which equals 1. And that 1 is the STP cost for a gigabit link. All right, so then let's just continue on. Let's say that we had 100 megabits, not 1,000. 1,000 divided by 100 is 10. Our cost here is going to be 10. That would continue on to 1,000 divided by 10 for our 10 megabit link that normally supports an Ethernet connection. In that case, the cost would be 100. And this can go on all the way to a 56K link if we had it. Now understand that WAN links are not common in our STP domain, but let's say that you had one, then 56 divided into 1,000 is going to give you 17,857, because it wouldn't be, this is 56K, so the representation would really be 0.056 megabits per second divided into 1,000, which gives you this value. Now, luckily enough, we don't have to do this math. These values are already set up for you as default within your device. I just want to let you know how you arrive at those values. Let's write in our cost above. So we have a cost here of 1, a cost on this link of 10, this link has a cost of 10, and this one has a cost of 100. So now as we're calculating our route path cost for this specific switch here, out of port, let's level the ports. Let's say this is port number 1, this is port number 2. Out of port number 1, we have a cost of 10 plus 10 plus 1. So our total cost, because it's cumulative from that port over to the route bridge, is going to be 21 out of port number 1. Now for port number 2, we're going to have a cost of 100 plus 1. So even though it's fewer hops, this isn't hops in the sense of routers, but layer 2 hops, it still has a higher cost because that's 101. So knowing that our devices have a loop potential here, one of these links has to be shut down and the other allowed to forward, we're going to shut down this link based on the fact that port number 1 has a lower cost to get back to the route. The calculation of each of these costs and the blocking of the different ports happens transparently to you as an administrator, and it's behind the scenes as soon as you set up STP, and actually it's pretty awesome. But now if you want to be involved in that and you want to define one path above another, even though it is faster, in other words, if you wanted this 100 meg pipe here to actually be the blocked port, and allow traffic to flow down this port for whatever reason you may have, you can actually set this cost to be lower. In other words, we have 21 of the as an accumulative cost between this switch on port number 1 and the route bridge. Now we're going to see if we can set port number 2 to a lower cost than the 21. Let's get into our switch to do that. The first thing we're going to do is we're at the main menu and we're going to opt for P, and the P is for port configuration. And we're going to pick a port here. So let's pick port number 2, just as we were talking about in our diagram. Look at the option here, C, for path cost. Right now, as a default, it's set to 100, which lets you know that this is a 10 megabit link. All right. Now, if we hit C, we're going to go in there and it's going to explain to you that this path cost is a 2-octet value. These are the values that you can go between 0 to 65,535. And it tells you about how you're setting this. In other words, the lower is better. But then it lets you set it to whatever you would like. So in this instance, if I want to beat 21, I could actually set this path cost, let's say to 10, so it'll match the others. Hit enter, and now my new path cost here under C has moved from 100 to 10. So what effect would that have on our diagram? Now that we have this link changed to 10 as a path, 10 plus 1 gives us a path cost of 11, which beats the 21, and now this is going to be flipped. This port is going to be shut down, and we're allowed to forward out of this port. This port that we have just chosen to allow to forward is going to be known in reference to this switch alone as its route port. Now every switch is going to have a route port, and it's simply the optimal path from that switch back to the route bridge. In other words, normally it's the route path cost that is the lowest that is going to be assigned the indicator of the route port. So let's look at our next whiteboard to go further in that discussion. Here we have our entire network complete with layer 2 devices, the route bridge. We've just gone through the calculation that lets us know that this port, port number 1, is going to be blocked. Port number 2 is going to be allowed to forward. So this is going to be the route port. For this switch here, we had a 100 meg link coming in, and we had a 100 meg link here with 10 meg here. It would go through that same process since it has two possible links to get back to the root bridge, and it would come up by saying that this port here, let's say port number 1 again, is blocked. Port number 2 is allowed to forward traffic, so this would be the root port for this specific switch. Remember, it's happening on specific switch instances, so it's not one root port for the whole network. All right, and then this device, this switch here, is going to have a root port, and it only has one choice because it has one link directly connected back to the root bridge, so that's the root port. The other thing we need to talk about is designated ports. By definition, when you have a root bridge, every port that you have coming out of that root bridge and making connectivity with any other layer 2 device is called a designated port. So we're going to have designated ports throughout. So you can see now that we're not labeling the link, we're labeling the ports, because one link will have a root port on one side and a designated port on the other without any problems. The rule for designated ports in reference to a root bridge was pretty easy. It's all ports connecting to another layer 2 device. It gets a bit trickier when you're talking about a layer 2 device that is not the root bridge. It's defined as all ports connected to layer 2 devices except the root port. All right, so this is going to be a DP as well, and this is a DP for designated port. Now the reason we're making the distinction connected to layer 2 devices, you've got to remember, we're talking about switches, so they can have hosts on the end here, and these hosts are not going to be serviced by root ports or designated ports as much as we really want that distinction to exist here between the layer 2 devices. So here we have another link that is an example of a root port on one end and a destination port on the other. So you see a pattern that we're developing here. All ports that are leaving from the root bridge out towards the end of the network are designated ports. You see them, the outward facing ports. All ports that are facing inward back to the root bridge are root ports. And it's pretty much as simple as that. The last section of this nugget deals with convergence. The idea of convergence is somewhat like the convergence we dealt with routing protocols. You remember IGRP, EIGRP, things of that sort? The process is simply this. You need to be able to recognize change within the environment. Once change is recognized, have some mechanism to pass that information between the pertinent devices so they can be updated, and then recalculate the algorithm, whether it's a routing protocol algorithm or it is the spanning tree protocol algorithm. You simply recalculate at that point. So let's get an idea of what happens. I'm going to show my connectivity as this network has existed. We'd already defined the center of our network to be our routing bridge here, and then we've assigned routing ports and designated ports throughout the network so that we are loop-free. We still have the capability of redundancy. In other words, if the other portion of our loop went down, the primary portion, then we could ride the backup system. And now we're going to interject a new switch into the network. Once this new switch runs through its post-operation, in other words, the power on and self-test, it's going to identify a specific port that is able to be up and running and connected to other devices. And here we have that port. And then it's going to send out a BPDU announcing itself, saying, you know what, I have a sending bridge ID. I don't have a root bridge ID in this specific BPDU because it doesn't have any knowledge of this root bridge as of yet. So it sends it out, and that's going to be identified as a change here. It's going to be sent from directly connected layer 2 device to other directly connected layer 2 devices. So down these links until you have the information spread throughout this network environment. Once everybody's aware of it, there'll be a recalculation of who should be the root bridge, because it might be that administratively you have changed this bridge priority, which is part of the bridge ID, down to 1, let's say, and since lower is better, this is definitely going to be the new center of your STP network. And so you need these other devices to be able to calculate and be aware of that, and we switch that responsibility from here over to this portion of the network. There will be effects on the rest of the network as well, where ports would already be configured as root ports and others as designated ports. Those will switch now. And then the calculation for your loop-free environment, where one port may have been blocked in the past and one allowed to pass traffic, that may switch as well. All this is going to take time, and that's probably the biggest complaint with convergence, especially in an STP network, is that changes take quite a bit of time before your STP network is stabilized again. But it's time well spent, because afterwards you're guaranteed a loop-free environment. I say this because there is the ability to turn off FTP on a per VLAN basis, and even though that will save you some time whenever you're making changes to your network, you will sooner or later pay in network problems and looped environments within your layer 2 networking. In this nugget, we started out by defining the main function of the spanning tree protocol to be to allow redundant paths, but at the same time prevent layer 2 loops in your network. We also talked about the fact that Cisco devices use the IEEE standardization of STP called 802.1d. Then we looked at the port states. We saw that we had the blocking state, the listening state, the learning state, and the forwarding state. Each of these states were important in understanding the switch's place within the network topology so that it wouldn't cause any loops in the layer 2 network. Next, we identified the bridge protocol data units as being key management messages used in things like the election of the root bridge and also calculating path cost from a switch back to the root bridge. Speaking of those two processes, here they are. First, the root election. Every device within the layer 2 network is going to send out its bridge ID and a BPDU. The bridge priority and the MAC address are contained in there. Those two pieces of information are going to be used to elect a root bridge. The lower the number, the better. Then we have the root path cost. This is the cost, a cumulative number from one switch over each of the layer 2 devices it needs to traverse back to the root bridge. And this number can be used to decide which ports will be forwarding and which ports will be blocking. And then we moved into the root and the designated ports. Simply put, the root ports point back to the root bridge and the designated ports point away. And the last section was on convergence. The fact that convergence can take a while, but it is necessary to implement a loop-free environment in our layer 2 devices. I hope this has been informative for you, and I'd like to thank you for viewing.